All right, this is the ratio test. This is another way of determining if an infinitely long list of numbers, when added together, it ends up adding to some finite number. And sort of the only way that we can possibly take this infinitely long list and have it all add up to something finite is if, well, first off, the list needs to eventually approach zero. Most of these numbers have to be really, really small in order for the sum of everything to still be a finite number. And as we've seen with a couple examples, it not only has to approach zero, it has to approach zero fast. So for example, when we have uh, a series like 1 over n, that actually doesn't approach zero fast enough. And when we're talking about the integral test, we can see this sort of has to do with the fact that the function 1 over n, or the function 1 over x, we use x's when we're talking about functions, n's when we're talking about sequences and series. The function 1 over x goes to zero slow enough that the area that we get, the area below the curve, ends up being an infinitely large thing. This is in comparison to the function 1 over x squared. Sorry, 1 over x squared, which looks very, very similar, but approaches zero faster. So because of that, the area under the curve is some finite number. And this relationship, this fact causes the series 1 over n to diverge, while the series 1 over n squared converges. And we saw both of these with the integral test or the p-series test, or what have you. This ratio test is talking about this idea of determining if our series approaches zero really fast. If it approaches zero really, really fast, we can go ahead and say that it converges, even if it's a little bit messy. So in other words, if we have some other series, so I'm going to use something like 1 over 2 to the x. And again, this is a series that we've seen, or this is a function, 1 over 2 to the n is a series that we've seen before. We've talked about it with the limit comparison test. The integral test would also work for this. Again, I'm just using this particular example because it's a relatively simple example. The advantage of the ratio test is that it can work on functions that you might not necessarily be able to integrate in the first place. Okay, but what the ratio test picks up on is it's determining if our function, or it's determining if our sequence is approaching zero really, really fast. And if it is, we can go ahead and say that the series, the sum of a bunch of numbers, ends up being some finite thing. Okay, so the ratio test is comparing n plus 1 to the n plus 1th term to the nth term. We're only focusing on the absolute values, and we're asking what is the ratio of these two terms as we approach infinity. So, for example, our example is the series 1 over 2 to the n. All right. So to determine this, we want to calculate this thing. The n plus 1th term over the nth term, and we want to take the limit as n goes to infinity. So the thing we're looking for is the limits as n goes to infinity of 1 over, the absolute value of 1 over 2 to the n plus 1 over the absolute value of 1 over 2 to the n. So in this case, all of these things are positive, so the absolute values don't matter. And we end up getting 2 to the n over 2 to the n plus 1 by dividing this through. And this thing ends up equaling 1/2. So in other words, this ratio, this L number, because this is 1/2, this means that it's small enough that it indicates that the series converges. So whenever you want to do a ratio test, you're trying to determine if the sequence is approaching zero fast enough. And this L, this limit, is an indication of how fast it approaches zero. So because this thing equals 1/2, which is less than 1, the answer is yes. This series converges by the ratio test. One other thing I wanted to point out with this is that this only, if L is less than 1, this converges. If L is bigger than 1, or if it doesn't exist, if it's infinite, then it diverges. If it equals 1, it doesn't actually help us at all. So I want to point out the first two examples I was talking about, the 1 over n series and the 1 over n squared series. So if we also want to know about the sum of 1 over n, if we calculate this limit, and again, the absolute values are going to end up dropping out. So we get 1 over n plus 1 over 1 over n. This limit ends up equaling 1. And this actually works for, the same thing happens for the n squared version. So this thing ends up diverging, and a very similar looking one ends up converging. Because they're both equal 1, they're in that approaching 0 speed range that doesn't actually tell us anything. The ratio test only works if we're approaching 0 really, really fast, as in like an exponential rather than like a polynomial.